All right, hey, it's Monday and I can't be there with you. Sorry about that. Going to the doctor. No big what. Um, but you guys have a quiz on Wednesday, so I wanted to throw together this quiz review for you so you could prepare and go over it with you now. So looking at number one. Um, Number one doesn't have a ton to do with the quiz, honestly. I just wanted to kind of review this old topic about relative minima and maxima. Those are on the quiz again, but we're not going to do anything like this about finding them from looking at a graph. We're going to do it more algebraically, but just to hit these ideas again, I wanted you to have a look and remember that for a graph like A, it just asks yes or no. Is there a relative minima on the open interval from A to B? And of course, this point stands out. You could build yourself, oops, that's way too big. You could build yourself a little window around it. And again, you have a relative minima as long as within that window, this y value is the least y value. And it definitely is. So this is clearly a yes. In this window, we could build, or in this graph, we could build a little window around whatever this x value is. Let's, whatever, mark it x. But as I look to the left and look to the right, that value there definitely is the least again, so this is another yes. This window, I mean, the smallest value would seem to occur here at B, but that's a hole, and it's at the end of an interval. And remember, this is an open interval from A to B, so it's A to B without including A or B. So there's no minimum there that we can use, so this is a no. And then the graph for D is a lot like B, except this time the low point is open. So this time if we tried to build a window around here, then that lowest point is a hole, which means it's not in our range, which means it can't be our min, which means this is a no. For part E, same deal again. We've got a node here, so we wouldn't be differentiable, but we're also undefined because there's a hole. So for lots and lots of reasons, we're not differentiable there. We also are not getting a min because that value is not in our range. That's a no. This guy's back to a yes because yes, we have a discontinuity here and we're not differentiable, but being differentiable isn't really the part. It's not part of the definition of having a minima. Remember we talked about how those critical points are where f prime of x equals 0, but it's also where f prime of x does not exist. So this is certainly an example of a place where the derivative doesn't exist because there's a discontinuity, but the function is still defined at some value, and that value is in our range, and that value is the smallest y value in this window, so that's a resounding yes. This guy would be a no again because that least y value is an open circle again, so that value is not in our range, so that's a no. And this guy's back to being a yes. This guy H is the same as E really, but E had a hole, so that minimum value is not in our range, but H has a solid dot, so that value is in our range, so it can be a local min, so this is a yes. And again, it's kind of like F, where yes, we have a min, even though the function's derivative does not exist because of the node. That one might actually be a cusp. So anyway, I hope that was pretty easy. That was just meant to be kind of a warm-up. And speaking of warm-ups, this one's kind of a warm-up too, just to remind you what the heck's going on with first derivatives and second derivatives. And so looking at this first graph, we can see that it's increasing, so you should certainly be answering that the first derivative is positive. We also see that we're concave up. So because we're concave up, you should be answering that the second derivative is also positive. And that's it. I mean, these are pretty easy. I hope you're just making decisions about the derivatives and second derivatives from the curvature of the graph. Since this guy increases, we've got a positive first derivative. Since it's concave up, we have a positive second derivative. And now that I've done that example, I assume the rest are kind of a piece of cake. Looking at number 3, we're increasing again, so the first derivative is positive, but we're concave down now, so the second derivative is negative. That's it. And then looking at 4, this function decreases, so the first derivative is negative, and this function's concave down, so the second derivative is also negative. And finally, this guy. Well, the function decreases, so the first derivative is negative, but the function's concave up, so the second derivative is positive. And I think that's probably pretty straightforward, so we'll move on. Okay, so finally now we get back to some algebra. These questions are asking you to find the absolute extrema for the following functions on the indicated interval. Notice these are closed intervals, so -1 and 4 are part of that interval. And that's important, we said, because, well, I don't know, say we had a function that did one of these. Then depending on where that closed interval puts us, if it ends here, let's say, and this is one of my endpoints, and let's say it starts here, let's say, if these were the ends of that interval, then I'm hopeful you can see that surely this point here would be a critical value, right? Let's say that point right there is, well, whatever. Let's say these are A and C. Then this guy in the middle is B. So our critical value here at B would be an absolute max on that interval, of course. But A and C have to be included as critical points too. We have to test them also. And so A, if we tested A, well, A's value would end up in the middle of all of these Y values, so that wouldn't be anything. But C would be the least Y value. So that end point would actually be the absolute minimum on that closed interval. So whatever critical values we find by setting the derivative equal to 0, like B, for example, we have to include our two endpoints as well, so like A and C, and then we have to test all three, because it's entirely possible that our absolute min or absolute max could end up right at the end of an interval. All right, so with all that said, let's do it. We can see that for number 6, the first thing to do is take the derivative, because we're looking for those critical values which come from the zeros of the derivative, or the places where the derivative does not exist. So for this function, my derivative is giving 2 minus 3 times 2/3, which is just 2 times x. Then if I take away 1 from the 2/3, I'm left with -1/3, and then would want to clean this up. So the -2x to the -1/3 would end up being 2 over the cube root of x. So because the exponent is negative, that's why I'm pushing this whole thing into the denominator. And because my power is 1/3, I'm turning it into a cube root. So now my 2 over here, I would want to get a common denominator, so I'd end up multiplying by cube root of x over cube root of x. This will allow me to combine these two terms into one term. I feel like we've done this exact problem before, by the way, which is kind of unfortunate, but that's okay. But this would end up giving, what, 2 times the cube root of x minus 2 all over the cube root of x. And I could factor a 2 out of the numerator, but honestly, I don't think I care that much. So to find the critical values now, we said that we'll take the numerator and set it equal to 0, and that will generate critical values. So if 2 times the cube root of x minus 2 equals 0, then that'll generate critical values. But we also take the denominator, and if the cube root of x ever equals 0, then our whole first derivative is undefined, but that makes critical values also. So we want to solve both of these equations. So for this guy, we get 2 times the cube root of x equals 2, because we'll add 2 to both sides. We'll divide by 2 to get the cube root of x equals 1. Then we'll cube both sides, and we'll get x equals 1. So that is now a possible critical value. Over here, we just cube both sides, and we get x equals 0. That is now a possible critical value. This is now the point where I double check that these solutions actually work, and I plug 1 not into the original function, or not into the derivative, sorry. I know that if I plug 1 into the original, or into the derivative, I'm going to get 0. But if I plug 1 into the original function, I don't really care what I get. I just want to make sure I get something. I don't want this function to be undefined when I plug in 1, otherwise 1 is extraneous. And I see if I plug in 1, I get 2 minus 3. That's a real number, so this guy's fine. And even 0 is fine. If I plug 0 into the original function, I do get some output. So It's not extraneous. It's fine. 0, of course, makes the first derivative come out to be undefined. That's the whole reason it's a critical value. He's a critical value because we know that the first derivative does not exist there. So we don't test it in the first derivative. We already know that that's a point where the first derivative does not exist. We test it in the original function to make sure that the original function does not exist. We need the original function to exist so that this point can be a critical value. Now they both are. So x equals 0 and 1 are both critical values, but don't forget what I just said earlier. The endpoints of our interval are 2. So -1 and 4 need to be added to our list. These are my 4 critical values. Now all I have to do is evaluate the function. And whoever's biggest is biggest, and whoever's smallest is smallest. So literally just find f of -1, and find f of 0, and find f of +1, and find f of 4. And the best way to do this is on your calculator. So I'll pull the calculator up. And how do I do this again? Turn that on. And then scroll that over. Great. So here's some function. It's not the right function, but we'll clear out what we've got. Go into y equals, type in the function that we do want. The function that we do want is 2x minus 3x to the 2/3. So that's right? That's great. So we zoom to a standard window. And the view from this standard window seems fine. And honestly, I don't even care what the graph looks like, because if I just want to evaluate these 4 values, the -1, the -1, the 0, the 1, and the 4, then the best place to do that is in the table, because in the table I can do all 4 real fast. Now if I go to my table, right now I'm set up for automatic, which I don't really want. So remember, we go into table setup, which is second function window, and set this thing to ask, the independent to ask. Leave the dependent variable set to automatic. We've done this before. You guys, I think, know how to do this, but still. Now when you go back to your table, it's blank, and you can type in -1, you can type in 0, you can type in 1, you can type in 4, and literally every answer that you want just pops right out. And I'll just grab that for later. So okay, so if I minimize that, it's gone. Great. So there it is. I mean, there's all your answers. I'll make this a little bigger, and we can see. Yeah, whatever. Okay, back. Sorry about the dog. The mailman showed up, so classic. Alright, anyway, these are the 4 y values. And they are -5. Whoops. 0, -1, and 0.4405. Okay, so based on that, I can now make my decision about who's the absolute max and who's the absolute min, and we can see that -5 is the absolute min. And I guess this is the absolute max. So in this case, both of our absolute extremes occur at the endpoints, right? These two relative extrema, relative maxima, and relative minima that we found that occur inside of the interval. Neither of those is absolute. And to drive that point home, I could show you the graphs. This was the graph that we saw. This was on a standard 10 by 10 window, so you wouldn't really want that. Throw that away. Here's the graph if we actually zoom into the right interval of x's. This is from -1 to 4, but you don't really want that either, because the y values are all kind of crushed up against the x-axis. So I'd pick a different window finally. I was zoomed in from -2 to 2, and suddenly now you know, our concavity is a little more obvious. We can see things a little bit better. One thing that's weird though, you may notice, is it sure as heck does not look like the graph is hitting the origin. See all that space between there? But we just did the math, didn't we? And we know that for sure we do hit the origin, right? We plugged in and f of 0 is 0. So this is just another lesson, and be really careful. Like, use your calculator. It's a good tool, but don't rely on your calculator too much, because sometimes what you see is not really what you get. But looking here, it is quite clear that our absolute min is down here, right? It's the value that we get at -1. Actually, I didn't even highlight it right. It would be further down. My window is not big enough to see that absolute min, but it would be down here occurring at -1, and the absolute max is right there, the 0.4405, which is occurring at 4. So everything we wanted to see is there. And then we've got one more graph we could look at if we cared, but don't forget you can use your calculator to find these y values. We could find the minimum that's at 1, 1, or 1, -1, but we shouldn't really be using our calculator to do it. We should be able to do it by hand. Notice we've got it here. We knew that at 1 there was some extrema. We could plug in 1 by hand pretty easily to find that that value is -1. So while our calculator will do it for us, make sure you're able to do it by hand. Anyway, after all this, remember that your final answer to me is a nice sentence. So I'm going to get rid of all this. Nah, I'll just push down, make a little more room. Okay, so your final answer to me, of course, would be, I might even type it, it might be faster. Yoink. All right, make sure you say f, not f prime, but f has an absolute max of y equals 0.4405, which occurs when x equals 4, and f has an absolute min of y equals -5. Which occurs when x equals -1. But that sentence there, right, or those sentences, that's the actual answer. Okay, great. This took a lot of time. I'll go faster on the next few, but hopefully by really showing you everything that helps you to understand. Moving on. Okay, so here's 7. 7 is obviously a different function, which makes the algebra a little different, potentially maybe a little harder, I don't know. But let's go see what we can see. We know the first thing we need to do is take the derivative. But before I do the derivative, I would rewrite this, because in the form it's in right now, I'd have to use quotient rule. I don't tend to like quotient rule. I'd rather just take this expression from the denominator, the x squared plus 2, just raise it to the -1 power. Now I'm looking at a product. Granted, it's now a product that has sort of a nested function and it will require chain rule, but even still, I think it's easier in this form than the other form. And we could disagree on that. If you guys would rather use quotient rule, that's fine. You may completely disagree with what I'm saying right now. That's okay. But for the first derivative, I'm going to go to town on this and say derivative of this is 2, and then this guy we leave alone. Then I'll add to that, I'll leave alone the 2x, and I'll differentiate this guy. So I multiply by the -1, and I get x squared plus 2. I drop that power by 1, so it goes down to -2, and I chain rule out a 2x. Yep. Okay, that's everything. Now from here we would need to clean up. This is going to be the biggest pain in the butt, I guess. But this would be 2 over x squared plus 2. If I resolve this negative exponent, then that just gets pushed back into the denominator. Then I see my -1 here, can just make this into subtraction. I see a 2x times a 2x making a 4x squared. And then I see a negative power that I would just take this base and push it into the denominator, x squared plus 2. And since the power is negative 2, this is going to be squared. Which tells me that from here, if I want to combine these two terms, I'd have to multiply this guy by another factor of x squared plus 2, and I'd have to do that on the bottom and the top. All right, so this first term, this is going to need some cleaning up. In the numerator, I'll distribute the 2, getting 2x squared plus 4. My denominator, though, those are going to now be common denominators, and I won't expand that. I'll leave that as x squared plus 2 squared, and that's fine. Notice I'm subtracting, 4x squared, 4x squared. So in my numerator, I can simplify a little bit, and I don't know, rather than having a negative leading coefficient, I'll just put the 4 first, so it'll be 4 minus 2x squared all over x squared plus 2 squared. And again, since my, the end of the line here is not this derivative, I just need this derivative so I can find my critical values and stuff. I don't totally care that this is simplified all the way. I could factor out a 2, maybe I could do some other stuff, but this is fine. I'll work with this as it is. And of course the next step is to find those critical values, and those critical values come from taking the numerator and setting it equal to 0. So 4 minus 2x squared. Anytime that equals 0, that'll be a critical value. And this denominator, anytime that equals 0, will be a critical value as well. So x squared plus 2 squared equals 0. So again, when the numerator is 0, that means the whole derivative is 0, which gives us critical values. When the denominator is 0, that means the derivative is undefined, or that it does not exist. Those are critical values too. This is why we split it up like this. Okay, so this means that 4 is equal to 2x squared. So divide by 2 and you get 2 equals x squared. Take the square root and you get plus or minus root 2 equals 0. Yeah, so those guys are potentially critical values. We do have to check to make sure that they don't make the original function undefined, because then they'd be extraneous, but for right now they seem to be on my list. Then this guy here, I would take the square root of both sides, I guess, and I'd have an x squared plus 2 equals 0. I'd subtract 2 to get an x squared equals negative 2. Then I'd try to take the square root, and I'd quickly realize that the only values of x that satisfy this are non-real. So no real solutions. And again, we've seen this plenty of times where we end up with a couple of equations and only one of them generates solutions and the other one doesn't. So that's fine, that's normal. So plus or minus root 2, are those valid inputs for the original function? If we come all the way back to the top, yeah, they seem fine. They're not going to cause any issues. Now the other thing to check, of course, is do they actually fit in this window? Because what if this window only went from 0 to 4? Then of course our plus or minus root 2, well, that's negative root 2 and positive root 2. Obviously the negative root 2 would get kicked out if it wasn't in our window, and if our window went from 0 to 4, then any negative values would get kicked out. But both of these values do fit in this window. By the way, root 2 is worth about 1.414. Just hit the buttons on your calculator. It's not bigger than 4. It's not less than negative 3, so they're both in that window. That also means we have two other critical values, the actual ends of the graph, which are the negative 3 and the 4. So my total list of critical values is that x equals, hold on here. Yeah, so we've got 4 critical values in there. X equals negative 3 because it's an endpoint, negative root 2 because it's a 0 of the derivative, positive root 2 because it's a 0 of the derivative, and 4 because it's an end point. So now I just test all 4 of those. In the original function, which is f of x, I'm going to just pull this down. All right, so we would want to find these four values, and we know that f of negative 3, f of negative root 2, f of root 2, and f of 4. Those are going to give us values, and again, we just want to find whoever's the biggest, that'll be our absolute max, whoever's the least, that'll be our absolute min. And the fastest way to do this is just to pull out the calculator again. So here it is. I'll go to y equals and I'll enter my function, which is 2x over x squared plus 2. And then go back to your table. You can clear out these old values if you want to, and then go negative 3, negative root 2, positive root 2, and 4. All right, so those numbers, I'm going to pull this out again. Those are the values we need. And negative 3 is giving negative, negative 0.545, negative 0.707, positive 0.707, and 0.4444. All right, so it turns out that the very, very smallest value, oh man, okay, sorry about that. This program, pretty glitchy. All right, this one is the least, and this one is the greatest. So these two, this time, the two values that are on the inside of the interval ended up being the absolute max and min. Remember from the previous problem, it was the two endpoints that were the max and the min. But this time we're going to say function f has an absolute max of, remember when you're giving the max you give the y value, so y equals 0.707, and then you say at x equals, and you tell me where it occurs, and it occurs at positive root 2, and f has an absolute, and you can't see what I'm writing, not that you need to, but still it's more exciting if you can. All right, f has an absolute min of y equals negative 0.707, which occurs at x equals negative root 2. And again, just because I think it's probably helpful, I'll show you some graphs. They're down here. All right, so again, this first guy is what I see if I graph on the standard 10 by 10 window. It's not so good, so I'll chuck it. I certainly would only want to see the window that I care about, the negative 3 to 4. And so if I change the x's to that, it doesn't look much better because again, the y values are too close to the x-axis. So I'll shrink my y scale to maybe only go from negative 2 to 2 or something. And if you look here, I guess I went from negative 3 to 3, but this is a decent view of the graph now. And it shows what we just saw. It shows that the two critical values that are in the inside of the interval, that point there and this point there, those are the absolute min and the absolute max. These points at the ends are not the very biggest or the very least, so those are not the guys we want. All right, and then I had another graph, I don't know why. Oh yeah, just showing these values again. We can see that at positive root 2 over 2, that's what this number is. We're getting our maximum value of 707, which I do think is just root 2 over 2. But there you go. So I guess what I'm saying is, I guess I'm saying I'm okay with this number being a decimal, because that is root 2 over 2. Am I okay with that? No, how about I just be okay with that, right? So you guys don't necessarily have to do it by hand. I don't want you to have to plug. I mean, it's not like it's hard, but if you had to do all of these evaluations by hand to get to root 2 over root 2 squared plus 2, This math isn't bad, but still, you get 2 root 2 over what? 2 plus 2 is 4. Reduce, reduce, you get root 2 over 2. So you could do it and get me this exact expression, but you know what? I'm officially saying decimals for the y values, those are fine. Now the x's, they should be exact, because the x's, you're doing the algebra. You're doing the derivative, you're solving by hand. Those x values should not be decimals. But if the y values are, I don't care. And I'll try to make that really clear on the quiz, that all x's should be exact, but y's can be decimals if they want. Okay. All right, again, I'm taking a long time here. Hopefully you guys are just fast forwarding if you don't want to hear this explanation, and hopefully if you do need this explanation, then it's helpful. All right, moving on. So number 8 is a trig function. Hopefully this one's not too ugly. Let's try it out. Although I did make it a little uglier than the other ones on purpose, because every trig function we've seen so far has just been 0 and 1. I didn't want that to happen this time. So let's take our first derivative, see how it goes. The derivative here would just be root 2. Root 2 is essentially the coefficient of x, right? X root 2 really just means root 2 times x. And our derivative would just be that coefficient. So this is giving a root 2. Then minus cosine would be minus the sine, or minus negative sine, sorry, of 2x. And then would chain rule out a factor of 2. And that's our derivative. We'll clean that up and we'll say this is a root 2. The minus minus will be a plus. We'll put 2 as a coefficient, 2 times the sine of 2x. And we'll set this equal to 0 and try to solve. And to solve, you'll subtract the root 2 first. So you get negative root 2 equals 2 times the sine of 2x. Then if you divide by 2, you get your negative root 2 over 2, which finally, this is me asking you to do a slightly difficult trigonometric function here, right? But we would say, all right, if we're solving here, then we're solving for the 2x, and 2x equals any angle where the sine of that angle is root 2 over 2. So we go to the unit circle and we think, where does sine equal root 2 over 2? And because sine is a y value, you know that it equals root 2 over 2 at any 45-degree angle that's down here below the x-axis. We're looking for negative y's. Those are down here. And the y's equal negative root 2 over 2 at these 45-degree angles. So who are these values? Well, if I rotate in a positive direction, this is 5 pi over 4. And this is 7 pi over 4. And if I were to go around twice, now can I go around twice? This is 2x, right? I don't know. Maybe I can. Let's do it, I guess. This would be what? 3 pi, which is 12 pi over 4. So 13 pi over 4. And if this is 13, then 14, 15. 15 pi over 4. Dot, dot, dot. So these are kind of the first 4 answers you get if you're rotating around and around. So really I'm just kind of counting. Here's 1, 2, 3, 4, 5 pi over 4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's kind of how I'm doing that. But don't forget, there is a little room for negative answers here too. Not as much room as there was for positive answers. But if I went negative, I would get negative 1 pi over 4 and negative 3 pi over 4. So 1, 2, 3, 4, 5, 6, 7, 8, maybe negative 9 pi over 4. That's probably too big at this point for sure. But here's a big old list of possible angles. And notice all of these angles are equal to 2x, so I need to chop them all in half. So if I chop them all in half, then I get plain old x equals negative 9 pi over 8, comma, negative 3 pi over 8, comma, negative 1 pi over 8, comma, 7 pi over 8, comma, 13 pi over 8, comma, 15 pi over 8. I know you guys kind of hate this method of mine, but here's a whole big long list of possible values for x. Now I only want the ones that live between 1 and 4, right? And so where would that be? Well, this is 3 divided by 8. That's definitely less than 1. Well, greater than -1 technically. But use your calculator. We can just look and see where these guys fall. So -9 pi divided by 8. Hopefully that's pretty obviously way less than 1 to you. That's like -3-ish. So that guy's out. But what about 3 pi divided by 8? That should also be obviously too big, because 3 pi is bigger than 9. And then you try to divide that by 8, you get a number that's bigger than 1, which means the negative version of that is still too small. So by doing that, let me move this calculator. Okay, by just kind of messing around, we can see that this number, 9 pi over 8, too small. This number, too small. But if -1 is our cutoff, then -1 is kind of here. And so negative pi over 8 is good. 7 pi over 8, what is that? 21-ish divided by 8? That should be 3-ish. That should not be too big, but we can check it on the calculator just in case. So 7 pi is that much divided by 8 is that much. That's only 2-ish, so that still fits. What about 13 pi over 8? That's 5, so sorry, that's too big. So that means only these two critical values actually fit in our window when all is said and done. But don't forget, the values from the window themselves count too. So before I run out of space, we again have 4 critical values. And the 4 critical values are the 2 endpoints plus 2 critical values that fell inside of our interval. So as far as critical values go, I'm seeing -1, and then negative pi over 8, and then positive 7 pi over 8, and then 4. And if those are the critical values, then those are the guys we have to evaluate the function. And this is my function. I would not want to have to do this by hand, so I'm not gonna, and I don't have to. So fit to width, scroll down. Oh, that's not what I want. Best fit, scroll down. Okay, so we've got our calculator. So the calculator makes this easy. We just go to y equals, clear out whatever's in there, plug in what we need, which is x root 2 minus cosine of 2x. Go back to our table, clear out the junk that's in there by hitting delete, not clear. Type in your -1, enter. Type in your negative pi over 8. Press enter. Type in your 7 pi over 8. And your 4. That's it. Those are my 4 outputs. So from those 4 outputs, I can decide who's the biggest, who's the smallest. Okay. So based on what I'm seeing here, let me make this even bigger. Nice and big. All right. So looking at these values. Oopsie daisy. Ugh. All right. Looking at these values, the biggest is certainly the 5. Which is occurring at 4, and the least is actually -1.26, which is occurring here. So this I kind of did on purpose too. Notice this time one of my endpoints is my absolute extreme, but one of my interior points is also an absolute extreme. The absolute min is an interior point, but the absolute max is an endpoint, which is fine. It's all whatever. Anything can happen. Let me make room to write out my sentence by whiting out all this extra crud. All right, but again, we're just going to say f of x has an absolute max of y equals 5.802, which occurs when x is 4. And f of x has an absolute min of negative 1.262, which occurs when x is negative 0.393. But of course we know that value of x, so we won't say negative 0.393. We'll say negative pi over 8. Let me actually write that out for you now. Alright, so we'll say f of x, or just f. I'll say f of x. So f of x has an absolute max of y equals 5.802. At x equals 4, and an absolute min of y equals negative 1.262 at x equals. Now remember, I care about x's, so don't give me the decimal. Give me that exact value that you calculated, which was negative pi over 8. That's everything. Looks like my y value got cut off a scotch, but I don't know if I care. There you go. So that's it. That's this trigonometry one. Hopefully that wasn't too bad. I assume it probably was kind of bad, but you kind of got to get on board. Not everything can be ones and zeros all the time. There's going to be root 2 over 2's and 1/2's and root 3 over 2's eventually. So review your unit circle. Moving on. Okay, 9. I think this one hopefully will be a little straightforward for us. We can go through this a little faster. For this guy, if I'm going to do the derivative, which of course I am, I would rewrite it first as a power function. So it'll be x squared plus 1 to the power of 1/2 instead of the radical. So now that I've rewritten it, I can do my derivative. And I just use the power rule. So I multiply by 1/2, leave the inside alone, drop the power by 1, so it goes down to negative 1/2. Now I have to chain rule out the derivative of the inside, which gives me an extra factor of 2x. So now cleaning the derivative up, the 1/2 and the 2x, they just kind of cancel each other to make x. And that'll be the only thing left in my numerator because I've got a negative exponent. So I'll push this guy down to the denominator, x squared plus 1. And he's got a power of 1/2, which I'll turn back into a radical. But that is it. This is my derivative now. And so to find my critical values, I'll do what I always do. I'll take the numerator and I'll just set that equal to 0. And obviously the only solution there is 0. So at least at this moment, 0 seems to be a critical value. I have to check it in the original function in a minute. But now I'll take the denominator, the x squared plus 1, square root of x squared plus 1, set that equal to 0. And before you even do any algebra, I hope you're thinking to yourself how x squared is always positive, and x squared plus 1 is always positive, and the square root of a positive isn't going to make 0. Only the square root of 0 makes 0, and x squared plus 1 never equals 0. So this thing pretty clearly is not going to have any solutions. But if you want to run through the math of it, you square both sides, you get x squared plus 1 equals 0. Then you subtract 1, and you get negative 1. And here's the reason we don't have any solutions. It's because you take the square root, and you're now looking at the square root of negative 1. And those, of course, are non-real. So it's not exactly that we have no solution. We just have no real solution. But for us, we only are concerned with real solutions, so we'll say no solution. That'll be fine. That seems to imply that the only critical value we have is 0. And if I test the 0 up here, yes, I do get an output. So that's my only value. Oh, we're not even doing absolute maxes and mins anymore. We're doing points of inflection. Okay, my bad. I just did more math than I needed to. That's okay. Because we actually need the second derivative now, kind of annoyingly. So since I need the second derivative, I wouldn't have solved this first derivative, or I wouldn't have simplified it so much. I would have canceled the 2 with the 1/2, that's for sure. And then I'd probably bring the x to the front. But I'd call this x times x squared plus 1 to the negative 1/2. But what I need is my second derivative. So we need to now find f double prime. And to find f double prime, we're going to have to apply product rule to this. So we'll take the derivative of x, just getting 1, and then we'll keep this other function, x squared plus 1, to the negative a half. Then we'll add to this x times the derivative of this guy, which will be negative 1/2. I'm running out of space, aren't I? Really quickly. Oh, didn't mean to do that. Okay, that should work. Alright, if that's too small, I apologize. I'll make it bigger again in a minute. But to finish off this derivative, we're multiplying by the power, so we get negative a half. We leave our base alone, x squared plus 1. We drop the power by 1 again. It goes down to negative 3/2. Then we chain rule again. We get another factor of 2x. So that's our derivative, as ugly as it is. And we need to clean it up now. Which I really don't want to do. This is pretty complicated. Alright, so it looks like I've got an f double prime. That equals. I've got this negative power, so this will be 1 over the square root of x squared plus 1. Then I do have a factor of negative a half, so the half will cancel the 2, but I still have a negative. So instead of plus, we'll say minus. Then I've got an x and an x, which makes an x squared in the numerator. And downstairs, we'll have the square root of this thing cubed. So x squared plus 1, I guess, cubed, and then the square root of that. Yeah, so okay, fine. An easier way to think of that, I would say, is with the cube. Oops, with the cube on the outside. And if you think about it like that, then really what we have is just 3 of these square roots. Over here we have 2 of these. Oh, sorry, we only have 1. So to get to a common denominator, wouldn't we just have to multiply by 2 more of these square roots? So that would end up getting a common denominator. This thing would be cubed as long as we had 2 more of these in the numerator. So x squared plus 1 square rooted squared, which, by the way, if you square the square root, you just get x squared plus 1 with no radical. So that means when this thing's done, our denominator is going to be an x squared plus 1 under a radical and getting cubed. And our numerator is going to be just plain old x squared plus 1 minus x squared. So the x squareds cancel, we just have 1 up there. So this is going to be a lot of work for a pretty anticlimactic finish here. But we already said this x squared plus 1, that thing never equals 0, right? I talked about it over here when I was solving. This thing had no solution. So when this thing is cubed, it's still not going to have any solution. It never equals 0. So our second derivative literally never equals 0. So no solution. Now what does that mean for us? It means our graph does not have any points of inflection. It's just always concave up or down. And so we can just test anywhere, honestly. So the original function has a domain of all real numbers. We could honestly just test anywhere. Essentially, you're building a number line that just literally goes all the way from negative infinity to infinity. So I guess we may as well just test 0. And who are we testing? We're testing the second derivative to see if it's positive or negative. And plugging in 0 gives 1. 1 cubed is 1. 1 over 1 is 1, and that's positive. So my assumption here is our graph is just always, always, always concave up. And guess what? If you look at the graph, here it is. We see that that's true. We're just always concave up. And 0 is where we have a minimum value, but that's not a point of inflection. We don't change concavity because we're literally just always concave up. So what does the question say? It said find the point of inflection. I guess our answer is f of x has no point of inflection. and f of x is concave up. On its entire domain, from negative infinity all the way to infinity. So again, we do a lot of work, but our final answer is this sentence that I just put in a box. You were asked to find the point of inflection. There isn't one. You were asked to comment on the concavity. So you'd say f of x is concave up, and you'd say on what interval, which is negative infinity all the way to infinity. And that's that question done. And here's 10. So 10 is a polynomial. This one should be fairly straightforward. We'll take our derivative, getting 6x squared minus 6x minus 12. Then I don't really care about the first derivative because this again is about points of inflection and concavity. We want to go directly to our second derivative, giving 12x minus 6. And we set that equal to 0. And we solve, getting 1/2 rather quickly. So the only point of inflection we have should be occurring at x equals 1/2. And then to test for our concavity, we just build a pretty basic sine chart. And 1/2 is the only 0 of our derivative. Yeah, so we're testing this guy, which by the way, if we factor out a 6, is just a 2x minus 1. So pretty easy to test. We'll plug in something like negative 10 or whatever, and we see that we're going to get a negative. And if we plug in like positive 10, we see that we get a positive. So based on these results, I'm ready to say that f has a point of inflection. Oops, what's the matter with me? So point PT of inflection, INF, at x equals 1/2, and f is concave up on the interval from 1/2 to infinity, and concave down on the other side of 1/2. So negative infinity all the way to 1/2. But that's it. By the way, I know that we're concave all the way to infinity because polynomial functions, which is what we are, their domain is always all real numbers, right? They don't have any restrictions. So it's not like we have to stop anywhere on our interval. We just are concave up all the way from 1/2 to infinity. And oh, by the way, if you don't believe me, here's the graph. And it's not super obvious where the point of inflection is, but maybe it is. Hopefully you guys can eyeball, that it's certainly happening right near 0. And it, I don't know, seems to me pretty obvious that it's probably right there at 1/2. So that's it. That's how that guy went. Number 11 is asking us to do the same thing, but this time we've got trig to deal with again. So let's do it. So we take our first derivative, and f prime is negative sine of x minus 1. Then we take our second derivative, and we get negative cosine of x minus 0. So we just have plain old cosine, which is good because that means this one will be easy again. But we'll go set that equal to 0. If we divide by negative 1, then we're just looking for when cosine is 0. Cosine is x values, so we're looking at the same points that we've been looking at pretty frequently nowadays, just pi over 2 and 3 pi over 2. Now again, we've got a window here to think about, but we're solving for actual x, so there's no dividing by anything or multiplying by anything, so any answer in this window is my answer. So that means from 0 to 4 pi basically means I want to take one trip around the unit circle, that's 2 pi, then take a second trip around the unit circle. So my 4 solutions are going to be the pi over 2 that I hit the first time around the circle, then the 3 pi over 2 that I hit right as I'm coming back. Then when I hit this again, that'll be 5 pi over 2. And downstairs will be 7 pi over 2. But all 4 of those answers fit in those first 2 revolutions around the circle. So all 4 of those values are potentially points of inflection. Potentially or definitely? I think they just definitely are. So okay, I can live with that. And discuss the concavity of the graph. So alright, I guess I have to build myself a sine chart again. And I need to plop all of these values on my number line. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So I've got 5 different intervals to test, but the good news is it's pretty easy to test these because all I care about is just plain cosine. My second derivative is, well, actually I lied. My second derivative is negative cosine because you have to use the original version. You can't use any simplifications that you did when you were solving. So that negative sign, that matters for sure. But basically think about these positions on the unit circle. As I rotate to pi over 2, I'm up here. Okay, forget that. If I'm a little bit left of pi over 2, right, then I'm... Okay, this is kind of annoying. Okay, left of pi over 2, but greater than 0, because that was the minimum of our interval. So somewhere between 0 and pi over 2 is an angle that rotated into quadrant 1. Forget about left and right. Remember, we're talking about the rotation of an angle. So somewhere between 0 and pi over 2 is here. Cosine is the x value, which would be positive, but it gets multiplied by a negative, so we're negative. Okay, cool. Then between pi over 2 and 3 pi over 2 would be an angle that rotated between here and here. So we're definitely left, so we're definitely negative. And if cosine is negative times negative, then we get a positive. And these should just switch back and forth, okay? Because from 3 pi over 2 to 5 pi over 2, that's the right side of the y-axis. So that's a positive value times a negative, making a negative. Then between 5 pi over 2 and 7 pi over 2, that should be a 2. We're to the left again, so we're negative times a negative for a positive. And then we stop at 4 pi, which again just means that from 7 pi over 2 to 4 pi, we're down here in quadrant 4 only. But cosine is positive there, times a negative is a negative. So cool, we can see that we've got 4 points of inflection. They're all 4 of the critical values that we found. And we are concave down from 0 to pi over 2, from 3 pi over 2 to 5 pi over 2, and from 7 pi over 2 to 4 pi. And we're concave up from pi over 2 to 3 pi over 2, 5 pi over 2 to 7 pi over 2. I'm feeling way too lazy to write that out, and this video is already an hour long, so I'm not going to write it out, but you guys can see what's happening there, I think. So after 11 comes 12, after 12 comes 13, and then we finally get to the last one, so okay, fine, I'll stick it out. Let's keep going. For this problem, we've got f of x. I would rewrite it before I differentiated it. It's going to be x plus just 4 times x to the negative 1. And then I can just do power rule on this to differentiate. So my first derivative is going to be 1 minus 4x to the negative 2. Then if I differentiate that, I can get to my second derivative, which will be 0 plus 8 x to the negative 3. I think that's it, right? So that should be easy enough, I hope. I would just set this equal to 0 and solve, trying to find my critical values. The 0 obviously doesn't matter. Dividing by 8 doesn't really matter either. Now this is actually what? 1 over x cubed equals 0. So the numerator has no zeros, and the only 0 of the denominator is 0. So the only critical value here is x equals 0. But that's a point where the second derivative is undefined, which is fine, that's legal. But if you bring it up to the original function, it's also a point where the original function is undefined, and that's not okay. So because this value makes the original function undefined, it's extraneous. And therefore there are no critical points. And therefore f has no points of inflection. All right, however, I should still consider my concavity. And my concavity is actually such that this place where the second derivative was undefined at 0, I should still consider it, because to the left of 0, I'm doing 1 divided by a negative number cubed, which does come out negative. But to the right of 0, I'm doing 1 divided by a positive number cubed, which is positive. So I do have two different concavities. I am concave down up to 0, and I'm concave up to the right of 0. So why isn't 0 a point of inflection then? Well, take a look at the graph. Picture's worth 1,000 words. It's because the graph has an asymptote there. So it's not a point of inflection, even though the graph changes concavity to the left and right of that asymptote. But you can't say it's a point of inflection because it isn't. So this question's a little more interesting than maybe we thought. And we do have to say f is concave down on the interval from -infinity up to 0, and concave up on 0 to infinity. So that's it. Your answer here is certainly this red stuff, where you're telling me that there's no point of inflection, and also this green stuff, where you're telling me about the concavity. And it's dawning on me right now, and I'm a little aggravated with myself, but you are, of course, supposed to be justifying these answers. So there's no point of inflection because the second derivative never equals 0, right? And f of x is concave down on this interval because f double prime is less than 0, right? Make sure you include those justifications. All right, that's 12. Let's do 13. Oh, 13 is just a polynomial, so yay, easy peasy. Because I take my first derivative, and I get 4x cubed minus 12x squared. Take my second derivative, and I get 12x squared minus 24x. And if I set that equal to 0, I should get two solutions. I can factor out 12x to be left with x minus 2. So pretty obviously 0 and 2 are my two critical values. And if I test them in the original, well, again, the original is a polynomial. Its domain is all real numbers. So neither of those is going to be extraneous. They're both critical values. They're both zeros. But that doesn't necessarily mean they're points of inflection yet. We still have to test them on the number line to make sure that our concavity actually changes. So we'll test 0 and we'll test 2. And to the right or to the left of 0, if I plug in something negative, I get a negative times a negative, which is a positive. In between, if I plug in something like 1, I get a positive times a negative, and I'm negative. And if I plug in something greater than 2, then I get a positive and a positive, which is a positive. So I do see the sign change for both of those values. So we would say that f has points of inflection at x equals 0 and x equals 2. And let me not forget to justify my work here, because f double prime of x equals 0 and f double prime of x changes signs. So make sure you give me all of that as your justification, don't forget. And we'll also say and f is concave up on negative infinity to 0 and 2 to infinity because f double prime is positive, and f is concave down on 0 to 2. Because the second derivative is negative. Uh-oh. All right, everybody turn navy blue. Great. All right, that's it. There's only one question left, and it's kind of an easy one because we just read the graph. Although I shouldn't say it's easy. These can be tricky. But it says the figure above shows the graph of f prime. You're looking at the first derivative. Of the following, which best describes the graph of f on the same interval? So it says 1 relative minima, 1 relative maxima, and 3 points of inflection. So the relative minima, those occur when the first derivative is 0. Now I'm looking at the first derivative. So those will be 0 here, here, and here. But I don't really get a minima unless we change signs. And I see my first derivative go from positive to negative, so yes, that actually is an extrema. We go from positive to negative, so that's the relative max. Now this guy is nothing because we go from negative to negative, so that is not actually an extrema. This guy, on the other hand, our derivative goes from negative to positive, so we were decreasing to increasing. That guy's a relative min. So now, just using test-taking strategies without doing anything else, I can see that I've got one of each. So C's out of here, D's out of here, E's out of here. But it's still down to A and B. We've got to figure out how many points of inflection we've got. Now, points of inflection occur when the second derivative is 0, and the second derivative will be 0 anytime the slope of the line drawn tangent to f prime is 0. So right here is a relative min. That should be a 0 tangent line. This guy that was nothing before, that's a 0 tangent line. This guy is another tangent line with slope of 0. And right up here, this one's annoyingly hard to say, but I'm going to go ahead and say that sure, that guy is another place where the tangent line is horizontal. But again, we need the second derivative to change signs too. And for this guy, even if that is 0, my function is decreasing and then decreasing. So that's a negative second derivative, negative second derivative. So this is not a point of inflection. But this guy is, because we're decreasing, increasing, so that's a change in sign of the second derivative. This is a POI, point of inflection. This guy's increasing to decreasing, so yes, that's a point of inflection. This guy's decreasing to increasing, so yes, that's a point of inflection. So it ain't 4, it is 3. The answer is A as in apple. So there. All right, hour and 8 minutes. Hope this was helpful. If it was helpful, tell me that it was. Give me some kind of feedback so I know that you guys appreciate this and want me to keep doing it in the future. But I hope you guys have a good Monday without me. I'll see you Tuesday. Bye.